Chapter 24 deals with nutrition, metabolism, and energy balance. So in this chapter, we're going to be looking at how the body converts the nutrients that were absorbed from the digestive system. How do they convert that into energy that can help you out, provide energy at the cellular level that allows the cells to carry out their main physiological functions, essentially to keep you alive. So when we look first at the nutrients, and this chapter is divided into different parts. So part 1 deals with the nutrients. This is substances that the cells require for growth, for repair, for maintenance. And we divide them into macronutrients and micronutrients. Macronutrients, there's 3 major subgroups of that. This is the majority of the food that you ingest. The 3 main macronutrients that you require are the carbohydrates, lipids, and proteins. Micronutrients are those, they're required but only in very small, minute amounts. This would be things like your vitamins and your minerals. Water is required for life, so technically you could say it is a nutrient. A lot of people don't think of it that way, but because it is a required component, it could be classified as a nutrient. Essential nutrients are those that must be eaten. They have to be taken in by your diet because the body does not make it. Non-essential nutrients are also necessary for life, but if there's not enough available for you to ingest, the liver can usually convert one nutrient to the one that's needed. So the liver is pretty good about the number of reactions that can occur there to convert from substance A to substance B. Energy is measured in kilocalories. 1 calorie is the amount of heat that's needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. In terms of how much of the different nutrients do you need, USDA has set up different guidelines, and yes, these have changed over the years. They'll probably change again later at some point. Currently, they're using what they call the My Plate. They used to use a food pyramid, now it's the My Plate. And the different foods represented are your fruits, your vegetables, grains, protein, and dairy. General principle is eat only what you need. Don't eat in excess. And you should be getting a lot of fruits and vegetables and whole grains, and then try to avoid junk food, which I know is easier said than done, especially when you're stressed out taking classes in college. So this is what the My Plate that the USDA uses as a guide. It gives you just a visual reference of how much you should be eating. In other words, don't have half the plate as protein. So we're going to look at those macronutrients first, starting off with carbohydrates. Most of your carbohydrates are coming from plants. One example is starch. Carbohydrates are your sugars, so they can be in different forms. It can be as fiber, insoluble, such as cellulose. It could be soluble, such as what you often find in some of your fruits. It's found in vegetables. It's found in some meat and dairy products. What's it used for? What are carbohydrates used for in the body? Glucose, which is the most common sugar, that by far is the preference for what cells want to use in order to get ATP. And why do they need ATP? They want that energy. So we'll see through this chapter, they can break down the proteins and lipids to get ATP, but given a choice, it's going to use, any cell's going to use glucose first. And there are some cells, such as your neurons and your red blood cells, that have to use glucose. If glucose is not available, then they'll start to die. Now, when there's excess glucose, it can be converted to glycogen. It can also be converted to fat, and then it can be stored. Animals do not make starch, Starch is the storage form of glucose in plants. And really the difference between starch and glycogen has to do with starch is long chains of glucose molecules all connected together like beads on a necklace. Glycogen also has glucose connected together in long chains, but there are branches on those chains. You do not see branching with starch. The recommended daily intake is 45 to 65% of the total calories from carbohydrates. You need to limit and not take in a huge amount of sugars. And a lot of the American diet exceeds this recommendation. A lot of the American diet will include rice, pasta, or breads. One reason for that is they tend to be inexpensive, so depending on which economic group you fall into, there's only sometimes so much money around and what you can afford to get. So we can say what these recommendations are, but that might not fit in with your budget from a realistic standpoint. This table just shows a summary for the carbohydrates, what the recommended daily allowance is, what happens when you have too much or too little of it. Lipids, these are your fats. One of the most common ones are your triglycerides. These can be found in meat, dairy foods, nuts. Cholesterol is also another type of lipid. It's found in egg yolk, it's found in meats, and various other types of products. The liver can also make some cholesterol. What are the lipids used for in the body? Adipose tissue offers a lot of insulation. It provides that storage. For fuel, it adds protection. Phospholipids are necessary in the production of the myelin and sheaths around your axons. Phospholipids are also one of the major components of any of your membranes, including the cell or plasma membrane. Cholesterol is necessary, and that helps to stabilize membranes. It's also used as a template for the production of bile salts and your steroid hormones. Lipids will help with absorption of your fat-soluble vitamins. So there's multiple uses and functions of lipids within the body. Once again, in terms of your dietary requirements, the American Heart Association recommends for fats to be 30% or less of your total intake of calories. The goal is to keep your cholesterol below 200 milligrams per deciliter. And this is a summary chart for the lipids, once again showing sources, what the recommendations for daily allowance, what potential problems if you have too much or too little. Proteins. Proteins come from a lot of different sources, oftentimes from animal products. They can also come from nuts, legumes, different cereal grains. And this table is showing the total protein needs that are, the list has amino acids that are necessary. You must get these from your diet. You cannot make them. You cannot get all of them, say, just from grains or all of them just from beans. You can get a combination of them by eating those two or containing those two in your diet. There's different uses for proteins in the body, structural and functional. Structural proteins are used as components in the skin, muscle proteins, connective tissue. It's also used from a functional standpoint. Some of your hormones are protein-based, and also your enzymes that are necessary for chemical reactions to occur are all proteins. There are different factors that will determine whether amino acids are going to be used to help synthesize or make new proteins, or whether it'll be burned as fuel itself. Some of these will be hormonal controls. Some of it has to do with if there's sufficient carbohydrates and fats in the intake in your diet. as to whether it will be used or not. Excuse me. Proteins do contain nitrogen in them, and so normally at homeostasis you have about the equal rate of proteins being synthesized as those proteins that are being broken down and lost. If you have a positive nitrogen balance, that means that you are making more protein. The synthesis exceeds breakdown. Negative nitrogen breakdown is the reverse, where the breakdown is exceeding the synthesis. You're breaking down more than you're making. This often occurs during infection or stress, or when an individual is under starvation. How much protein do you need? Well, it depends on several different factors such as age, size, what is your personal metabolic rate. Most Americans in their diet get more than enough protein in it. And here's a chart for the proteins showing different food sources, problems associated with excess or deficiencies. In terms of vitamins and minerals, these are the micronutrients. Vitamins are organic compounds that are necessary. These most function as coenzymes, meaning they have to assist the enzyme in order to get the reaction to occur. Most of them have to be ingested. However, there are some exceptions to that. Vitamin D, which is made in the skin. Some of your B vitamins and vitamin K, which are made by bacteria that are in your intestines. And then vitamin A, you need to have the ingestion of beta carotene, and then the body will convert that to vitamin A, and then the vitamin A is used. Beta carotene is found in a lot of your orange vegetables, like your carrots, your squash, sweet potatoes, things like that. But vitamins are going to be based or classified as either water-soluble or fat-soluble. The water-soluble ones are some of your B complexes and vitamin C. The body will use what it needs right then. Whatever's not used is going to be excreted from the body. So basically, if you have excess and it can't use that excess, say, of vitamin C, then it will be excreted in your urine. Fat-soluble vitamins are A, D, E, and K. These will be absorbed, and so they can be stored in the body, except vitamin K is not. The thing you have to watch with the fat-soluble vitamins then is if they are stored in the body when you have excess, that can lead to additional problems. So you don't want to have an excess of it. Too little is not good, but too much is also not good. During normal metabolism, oftentimes free radicals are generated that can cause damage to the tissue, and so some of your vitamins, such as vitamin C, vitamin E, vitamin A, act as antioxidants. That means they neutralize those free radicals. This is a table listing first all the water-soluble vitamins, symptoms if you have excess versus deficiency of it, and what's the function of it, and what's the major source of it. And then here are the fat-soluble vitamins. Several different minerals are needed, once again, in small amounts. There are 7 major ones: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. There are additional minerals that are needed in very trace amounts. You have to kind of balance the uptake and excretion so you don't end up with toxic levels of these. There are different reasons why these are needed, such as whether it helps with strengthening of the bones, whether it's helping with the thyroid hormone synthesis. Typically, your vegetables, legumes, milk, and some of your meats are very rich in these minerals. And here is a list, and then the trace minerals that are also needed. Metabolism refers to what is the overall combination of the reactions that are occurring in the cell. That's what metabolism is. It can be divided into one of two types. You have your anabolic reactions and your catabolic reactions. Anabolism is when you have small components and you are connecting them together to make something larger. So as examples given, you have amino acids, you connect them together to make proteins. That is anabolism. You have excess energy, and as you connect two things together and form a bond, energy is stored in that bond. That later you can break that bond in a catabolic reaction and release that energy. So catabolism or a catabolic reaction is where you're taking a larger molecule or compound and breaking it into smaller ones. And when you break it into those smaller ones, you've broken a bond and thereby releasing the energy. Cellular respiration is a process that occurs down at the cellular level. It is a catabolic reaction, so you are taking larger substances and breaking it into smaller substances. The classic example of this is you are taking glucose and you are going to break that glucose down. When you break the bonds, it's releasing the energy, which is what the cell needs. That's the whole purpose of why you're going to break things apart, is releasing that ATP, releasing that energy so the cell can use it. Now, in the case of cellular respiration where you are breaking glucose down, glucose is a 6-carbon compound. You're going to break that down and ultimately release carbon dioxide and water and ATP. Phosphorylation just refers to, oftentimes in these reactions, you are shifting some of the phosphate groups around with the ATP. Now, to process any nutrients, there's 3 main stages. Stage 1, digestion, absorption, and transport to tissues. So the digestion occurred most of it occurred in the small intestines, and then it was absorbed. It's transported in the blood. And remember, it goes to the liver first for basically filtering and detoxification, and then it's sent to the rest of the tissues. Stage 2 is cellular processing. This will occur in the cytoplasm of the individual cells. This is where either you're going to, from the nutrients, synthesize or make lipids, proteins, and glycogen, or you're going to have catabolic reactions occurring, such as glycolysis. And then step 3 is what we call the oxidative breakdown, where you finally produce carbon dioxide, water, and ATP, and this is going to occur in the mitochondria. So when we talk about cellular respiration, we're talking about glycolysis, or that catabolic reaction in stage 2, and then all of stage 3. And this is showing where these different processes occur. So it's stage 1 that's occurring in your digestive system. Stage 2 is in the tissue cells. Stage 3 is in the cells, specifically in the mitochondria. And this is kind of showing a simplified version of cellular respiration. If you start over on the left side of the screen, this is looking inside a cell. The white area would be the cytoplasm, or the cytosol is the fluid. So you're inside the cell. You have glucose. In the process of glycolysis is taking that glucose, which, as I said earlier, is a 6-carbon compound. It is about a 10-step process to produce pyruvic acid, which is a 3-carbon compound. So you've taken that glucose and you've generated now 2 pyruvic acids. In the process of glycolysis, you had a net gain of 2 ATP. In the very first couple of steps, you actually require the input of 2 ATPs, but later on you generate 4, so your net gain is 2 ATPs. You also generate 2 NADH, as you can see on the top of the diagram. These are electron carriers, so they're going to take a pair of electrons, transport them across now into the mitochondria to the very last step, and we're going to see those again. Meanwhile, the pyruvic acid is transported from the cytosol across the mitochondrial membrane, and now it's working in the interior of the mitochondria. Pyruvic acid is a 3-carbon compound. You're going to remove one of those carbons and form acetyl-CoA. Because you had 2 pyruvic acids, you'll have 2 acetyl-CoAs. Acetyl-CoA has 2 carbons. You also had 2 more NADH, those electron carriers, generated. So they're carrying a pair of, each one carries a pair of electrons. Follow the yellow line, and it's going to end up at the end on the right side, which we'll talk about again as well. So what happens to the acetyl-CoA? Well, it's going to feed into the citric acid cycle, which is occurring as well in the mitochondria. Now, the citric acid cycle, this is one of those things where I know it gets annoying. In biology, we call it the citric acid cycle. In biochemistry, they tend to call it the tricarboxylic acid cycle, and in microbiology, we call it the Krebs cycle. It's all the same thing. Why do we do this? I don't know. Maybe to annoy you students. I think we're doing a good job of it. But just so you know, because a lot of you will either be taking microbiology or have already taken microbiology, and you might be thinking that's the Krebs cycle there. Yes, it's the same thing with a different name. So the acetyl-CoA flows into this citric acid cycle. We'll use that name because that is what your book uses for this course. If I slip, I'm used to calling it the Krebs cycle, so if I slip, it's the same thing. Ultimately, you're going to produce 2 more ATPs here. You are going to generate 6 NADHs and 2 FADH2. FADH2 is another electron carrier. And as you can see, all of those NADHs, of which there are 10, and the 2 FADH2s, they all end up at what we call the electron transport chain and oxidative phosphorylation. This is where most of your ATP is going to be generated. Citric acid cycle generated 2. Remember, glycolysis generated 2. But in the electron transport chain, you're going to be passing off those electrons that were picked up in the previous steps. And through a process, essentially, this is where you generate ATP, and most of the ATP is generated here. Now, some books will tell you that the NADH will generate about 3 and FADH around 2. So they'll sometimes tell you anywhere from 28 to 32 ATPs are generated. The total yield is about 30. Some books will range up to 36. When you take microbiology, you may see 38. The difference there is, are you talking about a prokaryotic cell or a eukaryotic cell? Obviously, in A&P, we are studying your cells and your eukaryotic, where you had to move across from the cytosol into the mitochondria. That cost you some ATP. And so the general yield for prokaryotes is going to be in the low 30s, about 30 ATPs. For bacteria, which are prokaryotic, they don't have a mitochondria. So they can still carry out these processes, but they just do them a little bit differently. And actually, they get a higher yield of ATP. So they will generate about 38 ATPs per glucose. As I said earlier, the eukaryotic cells, which are your cells, typically, depending on the book you read, and it has to do with how much ATP is generated per NADH and FADH2. So it's going to tell you typically the total amount per glucose would be from 36 to 30 ATPs for a eukaryotic cell. This is an excellent video to watch. You can access it free on YouTube, and it goes through step by step. If you're a very visual learner, it's a very, very helpful video to watch on cellular respiration. Now, cells can't store a large amount of ATP, so as the levels of ATP start to rise, it's actually going to inhibit the breakdown of glucose because you don't need any more ATP, and instead it's going to promote, okay, we have enough ATP, we don't need to break down any more glucose, so let's store the glucose as either glycogen or fat. And that's exactly what's going to happen. Glycogen is formed when you have excess amounts of glucose. Mostly this will occur in the liver as well as in skeletal muscle cells. So glycogenesis is the formation of glycogen. Glycogenolysis is the breakdown of glycogen into glucose. It breaks the glucose molecule off, and this is done when the levels of glucose in the blood have decreased, when they're low, and you need to replenish it. Ideally, you want to keep the level of glucose in the blood relatively stable. You you don't want it peaking in sudden drops and back and forth. That's very hard on the body. So it's going to be maintained at a relatively ideally constant rate. So this is where, once again, the body makes those adjustments. And like I said, a lot of this has to do with the liver cells and some of the skeletal muscle cells. So glycogenesis is when you have excess glucose and you take that glucose to help form glycogen. Glycogenolysis is when you have excess or you have low glucose levels. So now, because you have that excess glycogen, break it down, releasing the glucose into the blood to get those blood levels back up. And this shows the relationship between glycogenesis and glycogenolysis. Gluconeogenesis is forming new glucose from non-carbohydrate sources. So it's not taking it from the glycogen that has been stored. This will occur in the liver. And what the liver can do, the cells there, they can carry out reactions where they can take glycerol and amino acids and combine them together to form glucose. The idea behind this is, once again, you don't want the levels of glucose in the blood to drop to extreme levels by any means. You want to keep it within that nice homeostatic range. And so it's kind of a backup mechanism to help protect you against very low blood glucose levels, which is hypoglycemia. It's a way of, okay, we don't have any carbohydrates that we can break down usually to glucose, and what do we need to do? We need more glucose in the blood so we can take from glycerol and amino acids and make it. And this is a summary of these different processes or different steps. Once again, the bottom line is to maintain a relatively constant level of glucose in the blood. For lipid metabolism, lipids actually give you more energy per gram than either glucose or protein. You actually get about 4 kilocalories versus 4 kilocalories for carbohydrate or protein. This is one reason why some animals we see tend to ingest a lot of fats to give them more energy, especially animals that are going to be hibernating. Humans don't have to worry about that, but the same process occurs that lipid releases more energy than carbohydrates or proteins. This is showing with lipid oxidation. Oftentimes you have triglycerides, can be broken down to the glycerol and then the fatty acids. The glycerol can be fed then through glycolysis. and ultimately end up with acetyl-CoA into the citric acid cycle, and fatty acids can also be broken down to acetyl-CoA as well. Lipogenesis, as the name implies, is synthesis of triglycerides, and lipolysis is the breakdown. So lysis is breakdown, genesis is the synthesis or building of it. Lipolysis, is accelerated when carbohydrate intake is adequate. At the cellular level, when the cells need energy, its first choice is always going to be carbohydrates. If carbohydrates are not available in any form, then what the cell will do when it needs energy is it will then revert to breaking down lipids. And so that's what's saying, when the carbohydrates aren't available, then you start to get the lipid or the fat breakdown. And this is a summary of the different reactions, either the breakdown or the formation of the lipid. Do you have to know all the steps? No, you do not. If you have an accumulation of ketone bodies in the blood that's associated with lipids, it can lead to ketosis. This is not something that you want to have happen. Lipids play a role in a lot of the structure of various components in the body. Phospholipids are used in the cell membranes. Cholesterol is used to help stabilize the cell membranes. Cholesterol is used as a template for the various steroid hormones. Cholesterol can also be used to help form the bile salts that are necessary for breakdown of lipids. For protein metabolism, proteins will deteriorate quickly, so you have to constantly be replacing them. The amino acids can be recycled. Proteins typically are not stored in the body like you see with the lipids and the carbohydrates. Remember, amino acids are the building blocks for proteins. So when you need to make proteins, you're going to have those amino acids there, because a protein is essentially just a chain of amino acids. And the site of where this occurs is on the ribosomes. It is going to be regulated or controlled by hormones, such as your growth hormones. Proteins are going to be involved with just about every aspect, every reaction that's occurring in the body. So over your lifetime, yes, you're going to be making an awful lot of proteins. And it's a nice balance of the catabolic versus anabolic. Usually it's what you call a steady state. You have the same amount being formed as you do that are being broken down. And this shows how the proteins fit into the overall charts of how components, when proteins are broken down, that some amino acids can be converted to keto acids, which can go to glycerol 3-phosphate, which can either then be shuffled over to glycerol for fats, or can continue through glycolysis. We can talk about the synthesis and the breakdown of these macromolecules, the proteins, carbohydrates, and fats, as though they're separate. But this chart really shows how they're all interconnected, which also means if you have a problem in one area, eventually it's going to affect the other two macromolecules. The absorptive state or fed state is when absorption of those nutrients is occurring. If there's excess nutrients, sometimes they get stored as fats if they're not going to be used. And so this is showing us it's being absorbed. Some of the major pathways from the digestive system of how the glucose can be shuffled into either adipose tissue or processed in the liver, stored excess as glycogen. Triglycerides are going to be stored in adipose tissue if there's excess. And then some glucose is going to be stored in the muscles also as glycogen. Amino acids that are taken up can be stored either in the liver or in skeletal muscle and made into protein that's necessary. Once again, you see all of the interaction that does occur. In terms of hormonal control, it's going to be controlled primarily by insulin. The beta cells of the pancreas are secreting the insulin, and the amount of insulin secreted is relative to elevated levels of glucose in the blood. So in other words, as that blood glucose level goes up, that stimulates the beta cells in the pancreas to secrete more insulin. Why? Because the insulin now released into the blood is going to help with the breakdown of glucose and the uptake of that glucose into the cells to try to lower it, bring it back down within the range. If there is inadequate insulin production or abnormal insulin receptors, basically what's going to happen is that you're not able to get the glucose into the cells where it's needed, and that excess glucose is going to be lost in the urine. It should not be there. And the glucose blood levels are going to be extremely high because the cells cannot get what they need. Instead of using the glucose, then the cell's going to be using fats and proteins, and this can lead to what we call protein wasting. It can lead to metabolic acidosis and weight loss. In the post-absorptive state, or the fasting state, now you've already absorbed everything, and you're starting the catabolic reactions of your fats, your glycogen, and proteins. Once again, the bottom line is you want to keep a stable level of blood glucose. You need to get the glucose available in the blood so the cells can have it, but you don't want to have these high spikes. So where is the blood glucose coming from? The first reserve is going to be glycogenolysis in the liver, and then in the skeletal muscle, finally lipolysis in adipose tissue and livers, and then catabolic processes of cellular proteins. So once again, showing how it's going to be used and the interrelationships involved. If there is, bottom line at the cellular level, if there is at the cellular level no glucose, no other carbohydrates, no lipids, then it will resort to using and breaking down protein for energy. This is not a good thing. At this point, you are at a level of starvation where you may or may not survive it. There's going to be both hormonal and neural controls at this level as well. The sympathetic nervous system is going to be interacting with several hormones, basically trying to reduce now the amount of insulin release as the blood glucose levels start to drop. So you don't want it all removed from the blood. So you're going to reduce the amount of insulin that's being released. It's kind of like, okay, we brought the levels down, but we don't want it down to zero. So this is once again showing some of that negative feedback that you have as the glucose levels are decreasing. The negative feedback goes back and turns off. Okay, stop releasing the insulin now. If glucose levels are low, adipose tissue can be innervated by the sympathetic nervous division to go ahead and release quick supply of glucose if necessary. This sometimes happens when glucose levels drop suddenly. It happens during the fight or flight response or during exercise. Other hormones such as growth hormone, as I said earlier, can have an indirect effect as well. So this shows some of the different hormones, what the effect is on the overall metabolism. In the liver, your hepatocytes of the liver carry out numerous metabolic functions. They're processing every type of nutrient that is passing through there, so they're having a huge role in helping to regulate the concentration of different levels of various compounds in the blood, storing vitamins, storing minerals. They're helping to metabolize anything that has been absorbed by the digestive system, so alcohol, drugs, hormones, bilirubin. So they're quite busy, and this is a chart just generally summarizing what some of those major functions are that occurs in the liver. This is one reason there's so many processes that occur in the liver. It's so important. A lot of medications can interfere with some of these functions, which is why, depending on what medication a patient may be on, every once in a while you need to run some tests to look and monitor that the metabolic function of the liver is not being compromised by medication that's on. In terms of energy balance, when you break a bond, remember you're releasing energy. When you're taking in nutrients and consuming that food, you're getting those large compounds that's bringing energy in. A lot of the energy is going to be lost as heat. So the remaining energy is going to be used to perform work by ATP, and then some of it's going to be stored. Eventually, when you want to think of it, taking that energy out of storage, using it, ATP, a lot of it is going to be converted to heat. What's that heat energy used for? Well, that's what's keeping your internal body temperature warm. It's helping to maintain that homeostatic balance. A lot of your metabolic reactions need to occur at a higher temperature than what you would think of as that room temperature. So our internal body temperature needs to be a little bit higher for these reactions to occur efficiently. Now, in terms of food intake, hopefully the amount of energy intake is equal to energy output and your weight remains stable. If it's not, then you're either going to gain or lose weight. Body mass index is a formula that they use to try to determine if a person is considered overweight or obese as compared to their weight versus their height. So it's not just looking at the weight, it compares to height. So if a person's BMI is 25 to 30, they're considered overweight. If it's greater than 30, then they're considered obese. Someone who is obese has a much higher risk of developing additional health issues and disorders. We are seeing a higher percentage of people who are overweight now than 20, 30 years ago. A lot of it has to do with the change in lifestyle, change in eating habits, change in food proportions. So this metabolic rate, as I said earlier, this is metabolism is the total amount of reactions that are occurring. So the metabolic rate is the total heat produced by all of these reactions that are occurring. There's a way that this can be measured. Usually it's measured, you can measure it directly, you can also measure it indirectly. It just, basal metabolic rate, or the BMR, just gives you an idea of how much energy is needed to perform your essential reactions to keep you living. You can measure this as well. It is going to be influenced by things such as age and gender, body temperature. Hyperthyroidism can cause a lot of different issues. What happens is the body tends to carry out catabolic reactions on a lot of the stored tissues and proteins. And even though a person seems to be always hungry and maybe eating more, because they're catabolizing all the stored fats and proteins, the person still seems to lose weight. Overall, bones can weaken, muscles, including the heart, can atrophy. Hypothyroidism is the reverse, where you have slowed metabolism, you tend to increase weight. Both of these can be treated if diagnosed properly. Regulation of body temperature. The hypothalamus is going to be really kind of the thermostat. Where is most of the heat being generated? That depends if you're exercising or if you're at rest. It does change. Normal internal body temperature is 37 degrees C or 98.6 degrees Fahrenheit. If you increase the temperature now, when you have an infection, the body is going to naturally, one of the responses is raise the temperature slightly. That can be good. It tends to tie up some of the iron in the liver, and most bacteria need the iron, and so they're going to end up dying. The problem is if the temperature continues to increase too high. It's one of those things. A little bit is good, but a lot is not. At higher temperature sustain, what happens is it causes proteins to denature, so that three-dimensional structure comes apart, they unwind. Structure determines function, so if you destroy the structure, they are no longer functional. So a denatured protein, you have disturbed the three-dimensional structure of it and made it a non-functional protein. Since a lot of your proteins are enzymes, then they can no longer be the catalyst for reactions to occur. If reactions can no longer occur, then the cell's going to die. In children under the age of 5, sometimes as the temperature increases, and especially as it starts to come down rapidly, can lead to convulsions or febrile seizures. Tissues can tolerate a lower body temperature much better than they can tolerate a higher body temperature. Core temperature, this refers to, when we talk about the core, the organs within the skull, the thoracic cavity, and the abdominal cavity. And the temperature there is fairly constant and is regulated very well. When an individual is sweating quite a bit and for a long time, they're losing water, but they're also losing salts like sodium chloride. And so they need to drink fluids, not just water, but they need to replace those electrolytes as well. In this, you may remember back from AMP1, showing with homeostasis how the body's going to respond if the internal body temperature is increasing. It's going to trigger the glands to, sweat glands to start sweating, releasing heat that way. The capillaries are going to dilate, especially along the skin, so that blood that has that heat in it, you have increased blood flow to the skin and you're losing heat that way. This will all help to bring the body temperature down back to normal range. If the body temperature starts to drop too much, then what's going to happen is it will trigger the blood vessels, especially on the superficial areas, to constrict, minimizing the amount of blood, thereby minimizing the amount of heat loss through there. Your skeletal muscles will be stimulated to start shivering, their contractions, because that's going to generate heat, bringing the body temperature back up. And all of this is going to be monitored and controlled by the hypothalamus. It's like your thermostat for you. So hyperthermia, this is elevated temperature. Heat stroke is when the core temperature has risen to about 41 degrees C. It's going to increase metabolic rates. The skin typically becomes very hot and dry. If not corrected, you can have permanent damage and it can end up being fatal. Heat exhaustion occurs prior to heat stroke. It's due to dehydration and low blood pressure. Once again, you need to get the body cooled. You need to rehydrate it. Hypothermia is low body temperature. Initially, it will shiver. After temperature drops too much, shivering will actually stop, can progress to coma and death. I said fever. It's usually due to infection. There are other things that can cause it, some injuries. Why do you get it? Because the macrophages release what are known as pyrogens. Um, and it's just like you going to your thermostat and you were cold, and let's just bump that temperature up a little bit. Essentially, that's what the pyrogen is doing.